So in previous class, we did talk about the case where, we have a conversion in probability, right? And then I want a very straightforward application, which is a weak large number, because the yn, which is sample mean, is a consistent estimator for the mu, right? Which is a very good candidate. And then we look at example for that, which is advise people don't gamble, right? Because the expected money they should return will be a negative number. And then today, let's look at another type of conversion, okay, which is conversion in distribution. So previously, consistency, we call a conversion in probability, okay, conversion in prob, okay, theta and head converge in probability to theta. So which means like with very high probability, the distance between your estimator and the theta, the underlying truth, can be as small as possible, okay. So if you choose give me a very small epsilon, if I get my sample size large enough, okay, this thing will be very close to 1. So we call conversion with high probability, a conversion in probability, okay. So people sometimes they say in different way, but it just tell you the same thing. Today, there are another type of conversion we call conversion in distribution. So this conversion is more familiar with you guys because you learn in calculus, right? So basically, like you have function f, x, and x here. So here, if you have sequence of random variable, you can think this sequence maybe just, y1 bar, y2 bar, y3 bar, right? So y3 bar equal to y1 plus y2 plus y3 divided by 3, right? And y4 bar, which is y1 plus 2y4 divided by 4, and so on, right? And yn bar, which is y1 plus 2yn divided by n, okay? So you can think that. So it's a sequence of random variable. And we say that it conversion in distribution, okay, to a random variable x here. So attention here, x here has nothing to do with n, okay? It has nothing to do with n. And we are shown by this notation, xn converge to x in distribution, okay, in distribution. Let me just highlight it. Okay. We call conversion in distribution. If we have the lim of n when n go to infinity, and infinity, and then the CDF of xn will convert to CDF of x, okay, x. So at that time, if we have this case, and then we say we have a conversion in distribution, okay. So let's look at this example. We have a fxn 1 to xn is sequence random variable. And this is the CDF of xn, okay, CDF of xn. And we show that xn will converge in distribution to the exponential at 1, okay, exponential 1. So with parameter 1, okay, theta equal 1. So let's look at this, okay, example first, and then you get a better understanding what does it mean here when we say conversions in probability, okay. So let's insert a slide. So just do some small basically is there further clarification, okay, about this sequence, and then we talk about that conversion, okay. So today, February 25, right? Oh, 26, I'm sorry, 6 already. So here is x1 to xn, okay? So x1 to xn is sequence of random variable, right? Random variable. And with the fxn, x equal to, so it's fxns, x equal to 1 subtract, right? 1 subtract 1 over n right? 1 subtract 1 over n and x for x greater than 0 and 0 otherwise, right? So what does it mean here? So this is a CDF, okay? This is a CDF for xn, okay? For xn. So if I look at the CDF for, how about CDF for x1? For x1. So x1, x, right? Will be equal to 1. This term will be 0, right? This term will be 0. Because n equal 1, right? In this case, n equal 1. Maybe I just write it here. 1x, right? X greater than 0. 0 otherwise. So basically, you just get 0 everywhere, right? Is that 0 everywhere? Oh, 1. 1 for x greater than 0 and 0 otherwise. So this is pretty much a step function, right? At 0, right? It will be 0 at for x less than or equal 0 and 1. It jump to 1. Okay, it jump right away. How about x2? Okay, I will go very slow. Okay, so this way you have a sense about what this is actually about. Okay, and x2 here, x will be right 1 subtract 1 over 2, right? 1, 2, 2x, okay, x greater than 0, 0 otherwise, right? And you can go for sure, you know, x3, x4, 5, right? So if x3, you just replace the n by a 3, right? x4, you replace the n by the 4. x5, you replace the n by the 5, right? And so on, right? And similarly, you can see also x n minus 1, right? X will be 1 subtract 1 n minus 1 n minus 1 x greater than 0 and 0 otherwise, right? And for sure, this way you can also go to xn, x 1 subtract 1 and x 0, 0 otherwise, okay? So you have a bunch of CDF like that, okay? So the question here that show that yeah, xn here is convert in distribution to x, okay? In distribution to x, right? So what does it mean here? If you look at definition, right? So basically you have to show the limit of f and x go to fxx, right? Basically you have to show that which is equivalent with limit of f n x, okay, will go to fxx, right? Right? For all x, right? For all x. And remember, know that, okay? So we have f n x, which is this guy, right? This f n x. And the x here, what is x here? X here in this case just exponential 1, okay? So in this case, we need to show it converges to exponential 1, right? So we need to show this is our x, okay? X. So remember that, recall that, okay? Recall that. When x follow exponential 1, right? fxx will equal to 1 subtract a x e to the negative x for x greater 0 and 0 otherwise, okay? 0 otherwise. Okay, so this, so basically our task is that we need to show the function, okay? This function. This function convert to this function, okay? Convert to this function, right? When n go to infinity, right? So if we can show that, and we're done, right? We're done. So for the otherwise case, obvious, right? Because 0, 0, It's matching, right? Matching. So we do care about the case where non-negative, right? Positive, right? Positive. So know that, right? Know that when x less than equal 0, fnx, right, equal to fxx and equal 0. So you don't need to worry about that. But when x non-negative, right? And at that time, fnx will be equal to 1 subtract 1 over n to the nx, right? Does it converge to? We need to check that. We need to verify that it converges to the fxx, which is equal to this guy, right? Correct? It's familiar, right? 1 subtract 1 over n to the n, right? It's just the e, right? Is that the e? 1 plus you get the e, right? So 1 subtract, you get the e negative, right? Negative. So this is a famous, know that? Okay. Use calculus fact, okay? Calculus fact, which is 1 to the 1 and x will converge to, okay? Then we maybe star here, okay? We can get star, right? Get star. Verify, right? Verify. So which means it tells us for x less than equal 0, we have that happen, and x greater than 0, we have that happen. Or, right? So if mxx convert to fxx, okay, for all x, right? For all x. Or Sn convert to x in distribution, okay, distribution. Okay, so here a sequence of random variable x1 to xn, it converge in distribution to x, right? To x. Question here? Good. Okay. So now let's look at some relationships between conversion in probability and conversion in distribution. Okay. So there are some important property. We won't go over all the proof, okay, but I will try to go through some of the proof. So this way, you can see a connection between them. But basically, in a property, okay, if you go deeper and there are different kind of conversion. So here in this class, we talk about two types: conversion in probability and conversion in distribution. So it's pretty good enough for you guys to do a lot of things already. But there are more kind of conversion, which is conversion almost sure, conversion in case, mean square order, different type conversion, okay? And they do have a relationship with each other. But here, like we just look at two, okay? But say if you do a PhD in statistics, you see more. But at that time, you need more measure theory and topology to do those things, okay? So here, like basically, like the first property tells us conversion in probability is stronger than conversion in distribution, right? So if you have conversion in probability, so at that time it will converge in distribution, okay? So this is the first property, okay? I think we should we go over the proof? There's the proof here, okay? Yeah, but let's just look at it. Okay, first, okay. And then the second property is tells us, say, if you have a conversion in distribution, okay, in order to make a conversion in probability, another time you have to have the conversion in distribution to a constant, okay. So if you conversion in distribution, xn, okay, conversion in distribution to constant, okay, constant, not random variable, okay. And at that time, it will be conversion in probability. So what does tell 1 and 2 tell us is that like the two type conversion will be equivalent only, okay, only we converge to a constant, okay. So say conversion in probability always leads to conversion in distribution, okay? But the conversion distribution, to make a conversion in probability, then at that time, yeah, X must be a constant, okay? It must be constant, some constant C, okay? And in the third probability, we call Bort-Mantel theorem. This is also one very important theorem, okay? So say here, you can get like a vector, random vector, xn, okay? Conversion in distribution to X, okay? It can be that general. If you can, in order to show xn conversion in distribution to X, okay? The only, there one way to do it is that like, you can also show that the expected value of f of xn, okay, converge to expected value fx, okay, for all the bounded continuous function f, okay, where f is go from some Rm, right, which is a dimension of the random variable to R, okay, to R. So if you can show that, okay, and then you can also conclude that xn converge in distribution to X, okay. And there another property, which is property number 4, also very important, is that it tells us if the distance, okay, between a sequence yn to xn converge in probability to 0, okay, 0, and xn's conversion in distribution to X, and then the yn will also conversion in distribution to X, okay. So this is also one very important property. So it tells us basically like, you can borrow this gap, okay, to show this guy conversion to X, okay. So which means like instead of directly showing like yn conversion in distribution to some X, right? You can borrow using a gap, okay. So kind of bridge, this kind of bridge style. So you bridge with some xn, okay, and where the xn can convert can be shown conversion in distribution to X easier, okay, easier, and then you can also show it. So this gap, eventually when you write a test on your own, say you do PhD dissertation, you use a lot in district thing. Let's say, you develop a new test statistic, new distribution, right? And you want to show your distribution, say conversion to normal distribution, conversion to chi-square, whatever distribution, okay? Because like if you can show it conversion to some distribution, so basically like your proposed can be used, right, for practice, right? Because like when you propose any kind of new distribution or new test, right, you need to study that property. And one important thing is that you need to tell people how your distribution goes, right? What drive your distribution, right? Is that the chi-square, a normal, some well-known distribution, right? Maybe a new distribution, even a new, completely new distribution. But whatever reason is that you need to show this, right? And sometimes you show this directly, very strictly, right? And basically, like you do zero bridge, you go from yn to x1, xn, and from xn you go to maybe kn or whatever, and do one thing where it's easy to show. Okay, so you bridge the gap between, you can also achieve the task. Okay, that is a for very important property. Okay, so maybe I will show you one property. We do have in the note too. Okay, it shows very clearly. But basically, like yeah, I think we should go through some of the maybe at least maybe one or two. Okay, one or two. And this way, you see why these two can related, right? There are more property here. Let me see. If we spend too much time and then okay. Okay, so maybe just do one. Okay, do one and then otherwise property you can look at the note. How about that? You want to do one or two? This help you understand better a little bit why they related, right? So let's look at the first one, right? The first one. New slide here, maybe the February. Okay. 26 here. Okay. Yeah, this thing like it you know a lot of energy here. Okay, you should expect like, but if you can digest it, it will be very good, very healthy for your future. Okay. So here we may show that, right, the first property, which if we have conversion in probability, then we have conversion in distribution will follow. Okay, in distribution will follow. So let A for some A given A in R. Okay, R. And some epsilon positive. Okay, epsilon positive, and then we have F X N A. Okay. So basically, our goal is that we want to show the Fxn conversion to. We want to show that basically, like we want to show that for any for any given here, we want to show that Fxn. Okay, show that, right? So if we can show that, right, is the goal. Okay. Okay. Just the epsilon we use later during the proof, but basically our goal is that like for any given A, right, we can show that if we can show that Fxn of A converts to Fxa, right? And then we can achieve this task, right? Because we want to prove it converge here, okay? So we know that Fxn of A will be equal to probability of Xn less than equal A, right? This is easy. It's just a definition of the cumulative distribution function. But we do a little bit trick here. Less than equal A. Now we put the X, we implement the X in, okay, here. Yeah, all trick, smart people here, a lot of smart people here. So, they know they do all kind of trick to make things work. Okay. So now you just break it down by 2, right? It's valid, right? It's valid. And this guy, it just nothing else than we do a little bit of conditional probability here. Xn less than A, given that X less than equal to, I think given it should be just straight here, plus epsilon, right? And plus here, Xn less than equal A. Okay, you can verify at home too. Okay, each line of the new equation is a lot of talk. Okay, put out here. Okay, till you derive your own distribution, you understand. Okay, when I did my dissertation, I spent 3 months for only one line of equation. Okay, to get from one to another. Okay, I didn't understand, and I read a lot of books and talked to a lot of people until I went to conference and I got that line. So it's a lot of energy here actually. So basically, it will less than equal to. So added till this, right? Nothing special, right? Here you just do some conditional probability, right? Conditional probability here. A given B and B, right? B A and B. And the second one, I just keep it like that. And will be less than here. There's some thing here. X less than A plus epsilon. So if you can understand directly as a class, will be the best, right? But sometimes you don't understand it directly in the class, and then just go home and make a cup of coffee and think about that, right? To be thinker, right? Don't be a watcher, a copier. It's a machine stuff. So this thing, yeah, you have to think like a little bit, right? The first part, I think, is easy, but the second part, it just require a little bit thing here, okay? So this thing, nothing else than the fx a plus epsilon plus also less than x n subtract x greater than epsilon, okay? Epsilon. Okay. Similarly, so basically like, so we show that we have if x n a less than equal to f x a plus epsilon for some epsilon non-negative, okay, plus property of x n subtract x greater than epsilon, okay. Okay. Similarly, we also have, can show that if x a subtract epsilon, okay, less than equal f x n a plus epsilon. Okay. So yeah, so all the whole, okay, we have. How about this in test 2? You like it? Okay, yeah, let's do in test 2. Don't laugh, don't smile. I put in test 2, okay, for this proof. You must measure, right? You have to be smart. All must be both smart, okay? But often they don't make much money. Sad thing. Okay, so this is what we have. Okay. So you have this guy greater than this guy, okay, and less this guy, okay, less this guy. So now you let the n go to infinity, okay? So basically, like, you need to confirm, you need to check it, okay? Check this, okay? Now I will send out the note, but for sure, this is a popular proof, so you can always find online, okay? So take n go to infinity. We have f x a less than the lim in, okay, n infinitive f x n a and less than a lim sub, okay, lim sub n go to infinitive f x n. The lim in lim sub is a very popular technique. People they use a lot in deriving the distribution, okay, f x plus epsilon, okay. And since it's whole for any, since star, maybe 2 star here, hold for any epsilon non-negative. So which means basically we just squeeze it, right? Okay. So this is how we prove that. So which means if we have conversion in probability, and then we have xn with convergence in distribution, okay? So this is one of the proof, okay? So the technique here, they use, by, adding stuff to smooth things out, and then use some lim in and lim sub trick, okay, to get the conversion work, okay? Okay, so I'll see you in next class, and we probably do a 2, and then we also look at different properties. But all this property, a very important property, okay? If you have the intention to rewrite a distribution or the new test statistic, you need those two.